Okay, so this is a lecture on Pell's equations, which are of the form a squared minus d times b squared is equal to plus minus 1 for some constant square-free integer d. And this can be negative, but it doesn't matter because the solutions there are just going to be a equals 1 and b equals 0. So we're only going to consider positive d. And square free means that no perfect square divides it except for 1. And here we're solving for a and b. Now we can first try to examine some solutions to try to characterize the general case. We first work with d equals 2. One obvious solution here is just a equals 1 and b equals 0, because 1 minus 0 is 1. And then we can also see that a equals 1 and b equals 1 is a solution, because 1 squared minus 2 times 1 squared is equal to negative 1. If we continue further, we can find that more solutions are 3, 2, 7, 5, and 17, 12, and this will continue, but this is enough for now. And we can try to look for some pattern between these solutions. First, we can notice that if you look at these two numbers, their difference is 0. The difference between 3 and 2 is 1. The difference between 7 and 5 is 2. And the difference between 17 and 12 is 5. Also, 5 is equal to 3 plus 2, and 2 is equal to 1 plus 1, and 12 is equal to 7 plus 5. So it seems that if we have some a comma b, this value is going to be a plus b, and this value is going to be a plus b, which is a plus 2b. Now we can look at d equals 3. Again, 1, 0 is a solution because 1 squared minus 0 is just equal to 1. And another solution is a equals 2 and b equals 1. Then from here, another solution is 7, 4. And then after that, there is going to be 26. And 15, and this continues. And here the pattern is a bit different, but this is because we don't start with this 1, 1. Here we can see that 7 is equal to 2 times 7 is equal to 2 times 2 plus 3 times 1 times 1, and 4 is equal to 2 times 1 plus 2 times 1. And this does seem like it could be a bit hard to stumble upon, but if you look at this relation, you're actually seeing that from a comma b, you go to 2 times 1 times a plus, 1 times a plus 2 times 1 times b, comma a times 1 plus b times 1. And what we're doing here is we can go from a comma b to 1 times 2 times a, plus 3 times 1 times b, and a times 1 plus b times 2. And the difference here is that this becomes 3 because d is equal to 3, and this corresponds to the 2 over here instead of a 1, while this 1 corresponds to the 1 over here. And in general, if we have some solution a0 comma b0, this corresponds to the 1 comma 1 and the 2 comma 1. Then for any solution a comma b, so let's say we have a0 squared minus db0 squared equals plus minus 1, it doesn't really matter which. like if it's 1 or -1, and a squared minus b squared is also equal to plus minus 1, then what we're seeing here is that a0 plus d times b0 squared minus d times ab0 plus a0b squared is equal to plus minus 1. And this is, as of now, this is just an observation. We don't yet know why this is true, but it's actually not too hard to see by just expanding this. So by expanding this, we would get a squared a0 squared plus 2ab a0 b0 times d plus d squared b0 squared minus d times, and then I'm going to bring the d into this, like distribute it. So d times a squared b0 squared plus 2d times a0 b0 plus d times a0 squared plus b squared. These cancel, and we will be left with a squared times a0 squared minus db0 squared minus b squared times d times a0 squared minus db0 squared. And then this reduces to a squared minus db squared times a0 squared minus db0 squared, which, since this is plus minus 1 and this is plus minus 1, they will multiply to plus minus 1 as well. And so now we have a fixed way to find solutions to Pell's equations. But this is not, like, we do not know if these are the only solutions yet. We don't know why we're picking a0 and b0 to be 1, 1, 2, 1, those values. And we also don't really know why we're doing it in this way. So the main point of this is the main point of what I'm going to do from now is try to figure out why we are doing it like this and try to further understand the process. So one thing to note about a0 plus b0 and b0 plus a0b. So we have some setup of ab and a0b0, and then we're multiplying it like this and like this. And we, like, for example, if you have a plus bi times a0 plus b0i, which is completely different from here, but it's just a way of thinking about it. This expands to a0 times a minus b times b0, which we can also write as plus b0 times I squared, and then plus a0b plus ab0i. And in fact, if we multiply a plus b times the square root of d times a0 plus b0, a0 plus b0 times the square root of d, we just got these values. a0 plus b0 plus ab0 plus a0b times the square root of d. So this is a way we can try to, like, we can try to work with this expression instead of the recursive formula, because it's just much cleaner. Because instead of working with this complicated formula, we're just doing basic multiplication now. And from here, we can consider the system of numbers of the form a plus b roots d for integers a and b. We say that something is a unit. So let's say we're working with u. U is a unit. We say this, we define this to be when there exists some u primes such that the product u times u prime is equal to 1. And we do notice that this is to some extent similar to the complex numbers, but restricted to integers, which are called the Gaussian integers, by the way. So there you have a plus b root I for integers a and b, and you want to know when there exists, I'm sorry, a plus bi, not a plus b root I, and you want to know when there exists c plus di such that a plus bi times c plus di equals 1. And usually what will happen is that because for this to be for this to be a real number, you will need that it will be the conjugate times something. So some k times a minus bi. And we're not going to go further into the details of this. We're just going to use the same concept of the conjugate. And the reason it's useful is because if we look at the root d term here, if we have a and b, like a equals a0 and b equals negative b0, then we see that this cancels. So now consider some u equals a plus b root d. We define u conjugate to be a minus b root d. And in the complex numbers, you would define the magnitude of u to be square root of a squared plus b squared. But first of all, square roots are a bit harder to work with. And second of all, we're going to need to involve d in some way. So instead we call the norm of u as a squared minus d times b squared. And as with the conjugates, in the imaginary numbers and the magnitudes of those, we have that the norm of u is equal to the norm of the conjugate of u. Furthermore, this is equal to u times the conjugate of u. And now we claim that u is a unit if and only if the norm of u is either 1 or negative 1. So if first we show that if u is a unit, then its norm is plus or minus 1. By definition, there exists. So first we assume u is a unit.
What is a unit, Rohan? Maybe you want to define that.
Yeah, I defined that over here. It's a unit if there's another number u prime such that u times u prime is equal to 1. So now let u be some unit, then there exists u prime such that u times u prime is equal to 1. And to continue from here, we're going to need to use a fact about norm that is also really similar to magnitude in complex numbers. That norm of a plus b root d times c plus d root, that's a bad variable choice, plus x plus y root d is equal to the norm of a plus b root d times the norm of x plus y root d. And this can just be seen with a bit of algebraic expansion. This is equal to ax plus dby plus bx plus ay root d. So the norm is equal to ax plus d dy squared minus dbx plus ay squared. And then if we expand this, like what happened over here, we will get that this becomes a squared minus db squared times x squared minus dy squared. So now if u times u prime equals 1, the norm of u times the norm of u prime is equal to the norm of 1, which is just 1. And because the norms are by definition integers, we have that the norm of u divides 1. The only integers which satisfy this are plus and minus 1. So therefore we have proved that if u is a unit, norm of u is either 1 or negative 1. Now we prove the other direction. If norm of u is equal to plus or minus 1, then u times u conjugate is equal to plus or minus 1. If it is 1, then we are done because u conjugate is the value of u prime, and that is a number which, when multiplied to u, yields 1, so u is a unit. Otherwise, we have that u times u conjugate is equal to -1, so u times negative u conjugate is equal to 1, and again we are done because we have some number that is of the form a plus b root d that multiplies with u to 1. So by the definition of a unit, u is a unit. And now we have proved this claim that u is a unit if and only if its norm is plus or minus 1. Now we can try to find the smallest unit, and this is motivated in part by the fact that when we were working with d equals 2 and d equals 3, these manual cases, this is what corresponds to 1 because 1 plus 0 root d is just equal to 1. And then from there, I mentioned before that the selections of these seems a bit arbitrary, other than the fact that we know they're near the top. So we can justify this by saying that when we write it as 1 plus 1 root d, this is actually the smallest. But first, we need to show this in general and show that in general there is a smallest unit greater than 1. And we can not just assume this because there are infinitely many numbers of the form a plus b root d. So we can't just say that we can't just assume that there is a smallest number. For example, if we consider any numbers, for example, in the real numbers, there is no smallest real number greater than 1. So therefore we can assume this, and we have to find a way to prove it. But one thing we're assuming there is that there is even a unit greater than 1. We'll just black box this for now and assume it exists. So now consider a unit u0 greater than 1. This is not necessarily the smallest unit yet. And in fact, it won't necessarily be even at the end of this proof. Because u0 is greater than 1 and u times u0 is equal to norm of u, which we showed in this claim is plus or minus 1. We have that, sorry, this should be u0 times u0 bar and norm of u0. We have that u0 is greater than u0 bar and u0 is greater than negative u0 bar. Here we say u0 equals a0 plus b0 root d. a0 plus b0 root d is greater than a0 minus b0 root d. So then 2b0 root d is greater than 0 and b0 is greater than 0. Here we have a0 plus b0 root d is greater than negative a0 plus b0 root d. And then we have 2a0 is greater than 0 and a0 is greater than 0. And in fact, this works for all units greater than 1 because we have just shown it here. So then we can consider the sets of all numbers a plus b roots d with positive integers a and b that are less than u0 and greater than 1, but that's covered by the positive condition. So now we can find some restrictions on these. We just need to show that this is a finite set because any group of finite numbers will always have a minimum element. We can compare this to u0. Here, because this is greater than 0, we must have that A is less than U0. And because A is also greater than 0, we have that B root D is less than U0. So this is a bound on A, and this gives B is less than U0 root D, which is a bound on B. And then we have restricted it to finitely many possibilities of each A and B. So there are only finitely many numbers with positive A and B that are less than U0. Now we can pick the smallest out of all of these. We call this equals AM plus BM root D. The M is for minimum. And this is the smallest unit greater than 1. So from here, all that's left is to show that all the units are powers of these. And if there's a unit that is less than 1 but greater than 0, we instead consider 1 over u, which we know is also going to be a unit. And if it's -1, if it's between -1 and 0, we consider -1 over u. And if it's less than -1, consider -u. We call this value u prime. Then u prime is a unit greater than 1. So it suffices to show that out of all units greater than 1, they are all some exponents of um. And we can show this by induction. Well, not really induction, actually. It's an axiom of the integers that's really similar to induction, but its statement is a bit different. So this is called the well-ordering principle. It states that any non-empty set of the positive integers has a minimum element. And this is an axiom, so it's part of the definition of integers, so we don't need to prove it. It's just something we take it for granted. And now we consider the set of x for which there exists. So these are positive x for which there exists a unit between to the x minus 1 and to the x. Actually, no, between to the x and to the x plus 1. If this is non-empty, then we can take the minimum element and we call this k. Then there exists a unit between underscore m to the k and underscore m to the k plus 1. Because is a unit, we can say 1 over is such that 1 over times equals 1. And this is a perfectly valid number of the form a plus b root d because of the definition of unit. Then we have to the k minus 1 is less than u over which is just u times 1 over which is less than to the k. And this must also be a unit, because if u times u prime equals 1, then u over times u prime times is also equal to 1. And now we have two cases. Case 1 is k is equal to 1. Then we have a violation of the minimality of because then U over UM is a unit greater than 1 and smaller than UM. But we defined UM as the smallest unit greater than 1, so that would be a contradiction. And we say that this is because of the minimality of U underscore M. For case 2, we have k is greater than 1. Then we have that k minus 1 is in this set S, because we have this condition. So by the construction of S, k would also be in that set. And now this would contradict the selection of k as the minimum element of S. This contradicts the minimality of k this time, but it's still a contradiction. So we have our desired result that S must be empty. And therefore there can be no unit greater than 1 that is between any powers of UM. So all units greater than 1 must be a power of UM, and therefore all units in general are a power of UM, or the negative of it. And in that general case, negative exponents are allowed. So to give a quick recap of how you use these powers, for d equals 2, we have that the smallest solution. And I never actually proved that this is the small solution, but you can do it with a bit of computation. And this is 1, 1. I mean smallest solution greater than 1. This corresponds to 1 plus square root of 2. Now we look at the powers of 1 plus square root of 2. There is 1 plus square root of 2 to the 1 equals 1 plus square root of 2. 1 plus square root of 2 squared equals 3 plus 2 square root of 2. 1 plus square root of 2 cubed is equal to 7 plus 4 square root of 2. 1 plus square root of 2 to the 4 is equal to 17 plus 12 square root of 2. And we consider these numbers, and there's an implied 1 over here, and these numbers. And if we go back to the table we computed at the start, they're the same numbers as here. And we can do a similar thing for d equals 3. We have that 2 plus root 3 is a small solution. 2 plus root 3 squared equals 7 plus 4 root 3, and etc. And this will give us all of the solutions. And one thing to note is that these give us the solutions for positive a and b. If there's 0, that just gives. So if a equals 0, this gives no solutions, because d times b squared equals plus minus 1, and we're not working with d equals 1 right now. I actually didn't specify that up here, but if you work with d equals 1, then it turns out to just be difference of squares, and that is not, like, it is usually done in a much different way than Pell's equations. I think this same approach would work for it, but it's much more complicated than needed. So except for d equals 1, this cannot be true, because here we have a d must divide 1, and that is not possible. b equals 0 would give a squared equals 1, so a equals 1. And as for the negative a and b, since the equation is just a squared minus db squared equals plus minus 1, here, since they're both squared, it doesn't matter whether they're positive or negative. So there's some solution a comma b, and there's also negative a comma b, negative a comma negative b, and negative and a comma negative b. So this is the way to find all of the solutions to Pell's equations. And there is one assumption we made. Does there always exist a unit greater than 1? Because when I was showing that there exists a smallest unit greater than 1, I did that assuming that this is true. And it is actually true, but we are not going to cover that today. And it uses a completely different topic called continued fractions, which I will most likely give a talk on later. But for now, this is all, and thank you.
Thank you, Rohan.